Event interval probability analysis was specifically designed for in-service repairable systems, and it was first published 3 years ago, but it's widely applicable even in non-engineered systems. In aircraft, the system includes not only mechanical, electrical, and instrumentation, but training, documentation, human factors, ground support, anything that impacts the aircraft total system reliability. This study spans 75 years on 5 aircraft types with 13 total grounding decisions stemming from events such as crashes or emergency landings. There are 10 events that contributed to a grounding, and of those, the first opportunity to ground decision is obviously the most critical. There were 6 of these, 5 by the FAA and its predecessor organizations. The FAA and its predecessor organizations have an 80% error rate on these critical first opportunity to ground decisions. There were 2 different governing authorities involved in the Concorde crash of year 2000. Event interval probability analysis failed to ground the DC-6 first crash in 1947. And that would give about a 17% error rate for this analysis method. We'll demonstrate the analysis approach with Boeing 737 MAX data. The first step is to establish and evaluate a null hypothesis, and a word statement for the null might be the fleet is at least as reliable as the worldwide fleet. This is the worldwide jet commercial fleet. A mass statement would be events are created by a homogeneous Poisson process with events being independent, identically distributed exponential random variables with a failure rate equal to the worldwide rate at the time of the event. That means that we are treating our null as a repairable system that is repaired as good as new. Now, if we can reject the null, the alternative hypothesis would be that the events are from a system that is less reliable than the worldwide fleet. We will evaluate this null with 3 different methods. Only one is necessary, but we will do it with 3 methods so that you can get maybe better understanding of what we're doing by rejecting this null hypothesis and what it means. Typically, these methods, Poisson, simulation, statistical, process control, traditionally what we have done is applied these analyses on the data set. That means the data set has to be fairly large in order for us to get good statistical and probabilistic data for analysis, because those methods require a lot of data. But for many critical systems, 1 or 2 events will be all that we have. We want the minimum possible events. And so we have to have methods that will allow us to do analysis on 1 event or 2 events. And what we do here is do something of a reverse analysis, or coming at it from a different direction. We will actually do the analysis on the null hypothesis, then see how well our events, our particular events, our 1 or 2 crashes, how does that fit the null? If it fits well with the null, then we do not reject the null. If it fits poorly, then we do reject the null, and the degree to which our data fits the null is quantified with probability values or p-values. If we can reject the null, then we use simulation to determine the unreliability distribution for the fleet. And from that, we get the risk of continued operation of the fleet. We'll first evaluate the null hypothesis with a Poisson probability. This is the general form for the Poisson. X is the number of events in a particular interval, and mu is the expected number within that interval. So this is the general form. We change that to departures between events and mean departures between events, which is more appropriate for commercial aircraft. When we do that, this is the form. The MDBE here is for the worldwide fleet, and these are the two events, the first event DBE, the second event DBE by estimate. When we use this data, the first event PV1, and PV1 is defined as the probability of X or more events occurring within the interval of that event. And that gives us a low p-value, which rejects the null. If we look at the second event independently of the first, it too would reject the null with nearly the same p-value. Nearly the same p-value because the departures are close together. So either one of these by themselves would reject the null. However, the probability of two consecutive events that are quick is even less probable. And so if we look at that and look at PV2, which is defined as the probability of two or more events occurring within an interval that is the sum of the two events, we see that there's about 1 in 1,000 chance that these two quick events would come from came from the worldwide fleet. So again, we reject the null overwhelmingly. We'll now look at computer simulation to evaluate the null. This is the unreliability distribution for the worldwide fleet. This is our null hypothesis, or we can say that the null hypothesis is that the event that we're looking at came from this worldwide fleet distribution. When we intersect the first event departures, which was about 136,000 with this distribution, the area to the left is the probability that the first event of the 737 MAX came from the worldwide fleet. So we can reject the null hypothesis with a low probability value. Another way of evaluating the null hypothesis is with a statistical process control. Here we have the null hypothesis DBE distribution from the worldwide fleet. On the left, it's rotated 90 degrees, and the scales for this distribution are aligned with a statistical process control chart. The scales are in alignment. The points that we see here on the statistical process control chart, they are simulated historical crashes. And we can think of these simulated values as being drawn from this distribution. The first and second events for the Boeing 737 MAX are plotted here. And by control chart rules of 2 out of 3 points between or beyond 2 sigma being process out of control, the process control chart rules would reject the null hypothesis. What we had is not 2 out of 3, but 2 out of 2, and 2 out of 2 is not defined by control chart rules just due to lack of granularity. But by aligning the graphs, we can take the probability of 2 out of 2 quick failures. We can find the probability for that, and because these scales are aligned, we can get the equivalent probability for one crash. How many departures at one crash would equal 2 consecutive departures that are short intervals. So the 2 fairly quick intervals that are consecutive is the probability equivalent of one crash at about 5,900 departures. And by control chart rules, that too is a process out of control. Now that we have rejected the null hypothesis with 3 different concepts, we accept the alternative hypothesis. The 737 MAX fleet is less reliable than the worldwide commercial fleet with statistical significance. But we need to determine what is the fleet reliability in terms of a probability distribution so that we can determine the risk of continued operation. How quickly must we shut down the fleet? Immediately? Or can the fleet continue to operate for a period of time while the issues are being resolved? We will look at that with computer simulation, and we will explain that with the more familiar units of time. The cumulative failure distribution for a repairable system is set equal to a random number. Instead of using lambda, we'll use MTBF. They're the reciprocal of one another. We solve this equation for time, and that gives us a TBF sample. This process is shown here on the right graphically. We have a 0 to 1 random number. These random numbers are uniformly distributed, equal chance of being drawn. So we draw a random number. We intersect the graph by way of this relationship and get a time between failure sample. We do that numerous times and form a distribution. The MTBF in this relationship is important to determine is it a statistic or is it a parameter. In the distributions shown so far, this has been a single number. It's a parameter for a population mean, the worldwide mean in our case. Now that we have rejected the null hypothesis, the Boeing 737 MAX now has an unknown mean, so this is a statistic. This is actually a random variable that will be discussed in the next slide. With our alternative hypothesis accepted, now the issue is the second part of this process, and that is to get the unreliability probability distribution for the 737 MAX, and we will use the numbers. We will do that after our 2 crashes, and the departures between events for these 2 crashes give us an estimate of the MDBE for the 737 MAX after the second crash. But that's only an estimate. We will use this statistic in our DBE relationship from the prior slide, and we will use 2 different random numbers in order to generate 2 DBE samples for the 737 MAX. And we will average those to get an estimate of MDBE as a random variable. If we have only 2 data points, this MDBE will be a very broad distribution. If we had 200 samples, this MDBE would be a very narrow distribution. We take this MDBE and use it in the relationship another time using a 3rd random number in order to get a DBE sample for that will when we get numerous samples, this will form a distribution which will be the unreliability distribution for the 737 MAX after the second event. So and so this is the equivalent of the time between failure distribution if we were talking about failures in time. This is the failure distribution after the second crash using the 2 data points. The This is equivalent to the time to failure distribution. If we're thinking about time and failures as is the more common case, but this is the number of departures distribution for the 737 MAX. So from this distribution, we can get the risk of a third 737 MAX event for any number of departures. For the 3 days that the 737 MAX flew following the second crash, by estimate, there were about 3,600 departures. If we intersect that number of departures with the distribution, the area under the distribution to the left of that number of departures is the probability of a third crash occurring in those 3 days. The probability is 0.0475 actually, and so that was the risk of a third event occurring given the unreliability distribution of the 737 MAX after the 2 events. Let's look at how fleet grounding decisions are evaluated. Before we look at all of the decisions, we'll look at a couple to see how it's accomplished. There are 2 independent methods that we'll use: reverse decisions and logic. Let's first look at the DC-6. It was placed in service in 1947. Shortly afterwards, we had a fatal crash. There was probably an implicit decision not to ground because there was no evidence that it should have been ground. Physical, statistical, probability evidence of no kind. So it was probably an implicit decision. But about 2.5 weeks later, there was an emergency landing with the plane in flames, and it was grounded at that time. So the FAA and event interval probability failed to ground at the first crash. Event interval probability analysis didn't exist, but had it been there, it would have voted no, do not ground. But shortly later, we had another event, and the 2 events taken together led to a grounding. So given that this is a good decision, it means that the first decision was wrong. This first opportunity to ground decision is color-coded red. It's wrong. So let's look at using logic. We know that the reliability at 1 equals the reliability at 2. There was no change in the reliability in a 2.5 week period. R2 is deemed inadequate. Therefore, R1 is inadequate. Another reason for saying that the first decision is wrong. The 737 MAX, we didn't ground at the first event or the second event. This third event is when we did ground, and so reverse decisions, we said yes, let's ground. It means that the first 2 decisions must be wrong because we reversed the decision to the right decision. Simple logic. Likewise, the reliability at 3, 2, and 1 are the same. 1 might even be less reliable than 2 because of reliability improvement during this time period. Having experienced a crash, there may have been opportunities seized to improve reliability from 1 to 2. But we're saying that 3 is inadequate, therefore 2 and 1 is inadequate. A second method for judging these decisions to be wrong. Using the same logic, reliability at 0 is also inadequate for the same reason that it's inadequate at 1 and 2. And so we really are introducing unreliable aircraft into service day 1, and this point is expanded in reference 12. This table presents the raw data and the results for the study. The first column is the plane and the event for the plane system. the fleet, and in some cases the specific aircraft is used. DBE that existed at the time of the event is in the second column. MDBE for the worldwide fleet at the time of the event is in the third. Poisson and simulation p-values are in these four columns in the middle. Red font indicates a low probability value that would normally call for grounding the aircraft. The decisions by the FAA and the English and French equivalent for the Concorde are in this column. The event interval probability analysis decisions are in this column. Dark green indicates a first opportunity to ground event. Fatalities are on the right. Actual fatalities, the probability of an additional event due to flying unreliable aircraft, and the avoidable fatalities, both actual and virtual, are here. You see footnotes here in the paper that provide some additional detail, but all the detail for where this data came from and the analysis can be found at this website. The cost of wrong grounding decisions. There were 503 avoidable actual fatalities and 9.44 avoidable virtual fatalities. These comes from risk being probability times consequence. The economic, company, and industry impacts are indicated by the 737 MAX. And in general, anyway, these impacts are common knowledge. So we won't get into any of that. However, we can say that if we had grounded the 737 MAX upon the first event, these impacts would have been exponentially less severe. And if we had had a third event for which there was a high probability, the impacts would have been exponentially more severe. The false positive risk always is there when we use p-values, and there is about a 1 in 100 chance that we would have a false positive. That is, we would ground a fleet unnecessarily. But this risk of unnecessarily grounding a fleet is small relative to the economic, company, industry impacts and the loss of life. Conclusions are: new fleets are unreliable when placed into service, and unreliable fleets are grounded late. This may not always be the case, but it is the case for all the fleets that I've looked at. And this calls for some aggressive recommendations. Recommendations are the FAA and other researchers should repeat this study with better data, even extend this study to additional fleets. 2, the FAA should conduct this analysis upon all major events like crashes and plane-related emergency landings, and they should make the results public, both p-values and the departures between events associated with those p-values. Thirdly, the FAA should use p-values as a system performance metric when they certify a new aircraft. There should be a p-value below which automatic withdrawal of certification is assured, unless there is strong cause and effect data to the contrary. And fourthly, the FAA and aircraft manufacturers should apply the data analysis method to precursor events. Precursor events, for an example, is the DC-10 crash in 1974 in France. Upon that crash, it was reported that there were 1,000 events or issues with the cargo door that led to the failure. Had we been analyzing those precursor events, we would have brought attention to the troublesome cargo door prior to the failure. It's possible that had we considered precursor events, there's about 623 additional fatalities that may be avoidable. Thank you, and I look forward to your questions.